Hello again, my name is Tom Irvine and I'm the instructor for this series of shock and vibration units. And I would once again like to thank the NASA Engineering and Safety Center, NESC, and Dr. Kurth Larson for making this series of webinars possible. So today we're continuing on with digital filtering, and today we're going to learn a new application. We're going to use successive bandpass filtering to calculate a power spectral density from a time history. And this is a wonderful method for educational purposes. It really helps show what a power spectral density is really all about. Previously, we've calculated power spectral densities using Fourier transforms. But if we do successive bandpass filtering, then we're going to really learn the true meaning of a g-square per hertz. And this is a very educational method, but it's rather inefficient for general day-to-day use. So this is something that we're going to do in class. Of course, I'd also like you to do the same thing as a homework exercise. And it may be just a one-time thing, one-time exercise for you. So we're going to start off with a couple of review steps here. We're going to synthesize a time history to satisfy a PSD. So here's our famous NavMat P9492 PSD. We've already used it several times in our webinar series. So this is a log-log format. Along the y-axis we have acceleration, g-square per hertz. Well, that's really GRMS squared per hertz. And we're going to really talk about that today. And we've got frequency in hertz along the x-axis. We've got 4 coordinate points. And the square root of the area under the curve is the overall GRMS value, which in this case is 6.06 GRMS. So this is our power spectral density specification. So let's synthesize a time history. This will be a review exercise. And the coordinate points are already in a file called navmat_spec.psd. And we're going to do a 60-second duration. And we're going to have the choice from row 8, which is a delta frequency or frequency step of 2.13 hertz with 256 statistical degrees of freedom. Then we're going to save the time history and its resulting PSD. So let's go to our vibration data GUI package for MATLAB, and this is up to version 5.4 this week. So we click on power spectral density, time history synthesis from white noise. We've done this before. So this script synthesizes an acceleration time history to satisfy a PSD beginning with white noise. Our breakpoints are already in a file, and that file is called navmat_spec.psd. And we're going to use English units, and we're going to have a duration of 60 seconds. Let's go to our processing options, and this is where we're going to choose row 8, and you can see the statistical parameters for row 8. And let's go ahead and calculate. So we're going to synthesize our time history. Okay. That goes reasonably quick. And we get a whole series of plots that come up. And we'll go through these plots one at a time. Okay. Here is our acceleration time history. Acceleration g versus time in seconds. 6.06 GRMS, that's the overall level. And that's also equal to the standard deviation given that the mean value is 0. So if we zoom in on this signal a couple of times, we can see, yes, that is in fact a random vibration signal. We have the corresponding velocity time history in inches per second versus time in seconds. Again, oscillating about the 0 baseline. And the displacement time history. So we have displacement in inches versus time in seconds. Again, the signal oscillates about the 0 baseline. Now, if we take a histogram of our synthesized acceleration time history, it's a bell-shaped curve, or you could say a normal distribution or Gaussian distribution. So that's all looking well and good. And here we have our resulting power spectral density. So we've got G squared per hertz. It's really GRMS squared per hertz. Frequency in hertz along the x-axis. Our red line is our specification. That's the nominal specification from the NavMat spec. Now the black line, there's two black lines there, and those are the plus and minus 1.5 dB tolerance lines. Now the blue curve is the resulting power spectral density of our synthesized acceleration time history. So our conclusion is that the PSD of our synthesis is falling well within the tolerance spans over the frequency domain from 20 to 2000 hertz. So we're good to go. We could take the corresponding acceleration time history, and we could put it into a shaker control system to do a shaker test, or we could do a modal transient analysis in a finite element package using that synthesized time history. So the next thing we're going to do is we're going to save that time history in our MATLAB workspace. So I'm going to call that Excel_th. Let me save that. And I'm going to skip over velocity and displacement. And then I'm going to also save the PSD just in case I need that for later on. Okay. So we're done with that PSD function for now. Let's go back to the slides for a minute or so. Now, I just demonstrated this exercise as part of this recording session, but previously I had done the similar exercise when I put these slides together. So the resulting time history may be a little bit different in the slide version. So here's the acceleration time history from the slide version. Its corresponding histogram with the bell curve shape. That's for the instantaneous acceleration values. And then the power spectral density of the synthesized time history. So that's all looking well and good. Now, the next thing we're going to do is we're going to get into the successive bandpass filtering exercise. So I've got a table here on the left, and this is called the full octave band frequencies in hertz. So for each octave band, there's a center frequency, as well as a lower band frequency limit and an upper band limit frequency. And in each case, well, let's just take the center frequencies here. This is the band center frequency for the band at 20 hertz. And then we go up in steps of 2. So multiply by 2 to get 40, multiply by 2 again to get 80, and so on. So these are called 1 octave steps. And then likewise, the lower frequencies and upper frequencies at least approximately follow that same pattern as well. And here's another thing to note. Let's say we have this first band here. Its upper band is 28 hertz. Well, that upper band limit becomes a lower band limit for the next octave band. Another thing to notice is that if we were to take the average between 14 and 28, just the straight arithmetic average, that would be 21 hertz. But instead of having 21 hertz, the center frequency is 20 hertz. And the way we calculate center frequencies relative to these two band limits is 20 is equal to the square root and then within parentheses 14 times 28. So the center frequency, I believe it's also called a geometric center frequency. But anyways, let's go on, continue onward to our filtering. So we're going to perform bandpass filtering for each band, and we're going to use the upper and lower frequency limits. And we've got our Butterworth filter, which we did that in our previous webinar. So we're going to go to our Butterworth filter. And then here I've called the file input_th, but Actually, I just named it acceleration_th. So I think I need to change that a bit. Let's. So here we have the. Well, okay. Here I call it input_th. We could, in the slide version, in the class version, I called it Excel_th. So that shouldn't really be a problem as long as we take note of that. Okay. So let's go ahead and do this successive bandpass filtering, and we're going to use this table as our guide. And we're going to go through each of the cases. For each of these, at 8, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we have 8 bands. So we're going to input our, we're back to the vibration data GUI package. And actually, before we do that, I'm going to show you one other thing. I've already taken those frequencies, and I've copied and pasted them into an Excel spreadsheet. And there's a reason for this. We're going to be putting our results in an Excel spreadsheet as we do this successive bandpass filtering. So let's go to time history, filters various. We'll do our Butterworth filter. It's going to be a 6-order Butterworth filter. For this particular purpose, we're going to turn off the phase correction. We're dealing with broadband, random, stationary, steady state type data, so we don't need to use phase correction. We will use bandpass filtering, and our input file is going to be Excel_th. That's our synthesized acceleration time history. It'll be acceleration in G's for the y-axis. We're going to start with the band that goes from 14 to 28 hertz. Now, before we actually do the filter, let's take a look at the transfer function. And we'll only do this for the first band. Let's skip over the real and imaginary components. So here's what we have. This is Butterworth bandpass filter, 6-order, 14 to 28 hertz. We've got the phase angle and the magnitude here. Now, if this were an ideal filter, instead of being this kind of plateau with the slopes that kind of round off, and then the downward slope. If this were an ideal filter, we would see something that was the shape of a rectangular box. But for practical purposes, having to do with numerical stability, we have to allow for some roll-off, both below and above the band of interest. And let's just to help understand what's going on, I'm going to put some cursor points here. So let's see, we're going from 14 hertz. So I'm going to try and get as close to I can as 14. Okay, that looks pretty good. Create new data tip. Let's go to 28. Okay, let's see, there's 28. So those are our two band edge frequencies. Now, you can see what's happening. We do get a unity gain plateau right here in the middle, around 20 hertz. But we are attenuating some of the desired frequency in this region, and we are also attenuating some of the desired energy in this region here. And we're also accepting some undesired energy below 14 hertz, as well as also accepting some undesired energy above 28 hertz. Well, again, that's just sort of the practical limitation and consideration for implementing a digital filter. This is a 6-order filter, and on my to-do list, I want to make an 8th-order filter as well, which would more closely approximate a desired ideal filter. Well, that'll be okay, but then we'll have to pay just a little more close attention to filter stability. Whereas with 6-order, this is just a good general purpose filter that's very stable in most cases. But let's go back to our time domain and let's start doing our exercise here with our successive filtering. So I'm going to click on the calculate response. So here's our bandpass filtered time history from 14 to 28 hertz. It's acceleration in g versus time in seconds. And if I go over to here, you can see, well, let's take a look here. These are two overall RMS values. So our input from our NavMat synthesis was about 6.06 GRMS. And you can see by filtering it, we get a much reduced level. That's because we're only accepting the energy between 14 and 28 hertz. So what I'm going to do is I'm going to copy and paste this, just do a Control-C, Control-V. And actually I already have the number in here, but I'm going to, for a reason, let me go ahead and copy and paste that anyways. Now, I've got a couple other columns set up. So the D column is always going to be the GRMS value from our filtered signal. Then we've got a GRMS squared column. And then the bandwidth is just going to be the upper minus the lower frequency, which, as it turns out, the bandwidth is also going to be numerically equal to the lower frequency. But I am being more proper, and I'm subtracting the A column value from the C column. The center frequency, well, that's just the B. So we got 20 hertz here, we have 20 hertz here. Then we've got GRMS squared per hertz. Well, what we do is we take this E column number and we divide it by the F column number, and that's the GRMS squared level for that particular frequency band as centered at 20 hertz. So from here on out, we're just going to fill in this table. And you might think, oh, this is just some busy work exercise. Well, maybe so, but it's a busy work exercise with a very important purpose. And I highly encourage you to do this yourself. Just do it once so you can learn about the underlying meaning of a power spectral density. So from 28 to 57 hertz, okay, the level is coming up a bit. So I'm going to copy and paste the overall RMS level. This is the corresponding bandpass filter time history. In each case, the filter data will have a lower RMS value than the input. Okay, so we go to our next band, 57 to 113. Calculate its response. Okay, copy and paste the number to Excel spreadsheet. Let's go to 113 to 226. Calculate the response. 2.2 RMS if I round off. And maybe we should just sort of stop and pause, and instead of just racing through this, let's kind of take a look at what's going on with this filter time history. So there's what a zoom in or close-up view of the bandpass filter time history is from 113 to 226 hertz. Okay, moving onward, we have 226 versus 453. Copy and paste the overall RMS value. Now, it turns out that so far, each time we go up to a successive higher band, the RMS level is increasing. And that is due at least partially, or maybe even due mostly, to the fact that we have a proportional bandwidth. So the higher we go in center frequency, the wider our band is and the more energy it captures. Okay, 453 to 905. Okay, that's, if we round off to 2 digits, by coincidence, it's numerically equal to pi. Pure coincidence. 905 to 1810. Okay. Now, for the first time, we've gone down a little bit in the RMS. Well, The reason for that is that our PSD function for the navmat has that downward slope for its third segment. Now we're going to go 1810 to 3620, and before we click the button, I want you to notice one thing here, is that our navmat spec goes to 2000 hertz, but which is just higher, which is just a little bit higher than the lower frequency edge. But this band is going clear up to 3620 hertz, so over most of this band there is no energy. Okay, so the next thing we're going to do is just do a bunch of fill down steps. So I highlight and double click on this little box at the bottom right corner. Okay, that's very good. And I might just play around a little bit. And so what we've actually done is with these last two columns, we've calculated a power spectral density function. And as I mentioned earlier, as we go up in band, in terms of the band number, our bandwidth is increasing. In fact, due to the 1 octave change, it's increasing by a factor of 2 each time. So this, again, is called a proportional bandwidth. Now the next thing we're going to do is copy and paste these points into MATLAB. So let's see if I can get my MATLAB up. And I've got a way for doing this. If you have a better way, that's fine by me. Use your better way. So I'm just going to call this BPF PSD. This would be our bandpass filtered PSD. And I'm going to put a bracket, and then I'm just going to paste all those numbers. Then I'm going to put a close bracket and enter. Okay, so now I have all these points called into MATLAB, and the way MATLAB scales the numbers, it's kind of a little bit deceptive. There really are non-zero numbers in that second column there, but the fact it's scaled by 1,000 there makes it appear all to be zeros within the stated number of significant digits. But let's go ahead and plot this power spectral density. And there's a couple of ways we can do this. But I'm going to show you my latest favorite way. Let's go to miscellaneous, plot utilities, and I'm just going to pick this multiple curve option here. And I've got this file. I call it BPF PSD. Well, this is our bandpass filtered method. So we did a bandpass filtered method to calculate our PSD. Now let's also call up our navmat spec. So to get our navmat spec, let's go back to vibration data, and first we need to call it into our MATLAB workspace. It's an external ASCII text file. So import data, and we're going to select our ASCII text file, and it's going to be that navmat spec PSD. And then, okay, so we've got to call it something for our workspace. So I'm just going to call it navmat. That's good enough. So I press after entering name, import complete. So I've now called up the navmat spec. I've read it off the hard drive, and it's in the MATLAB workspace. So I'm going to type in navmat, and I'll call this the spec. Power spectral density, or I guess you could just say PSD. I'm going to make it figure 7. Select both curves. X-axis label will be frequency in hertz. Let's make it a log-log plot. Y-axis will be Excel in G² per hertz. And let's plot the curves. Okay. So as I look at our bandpass filtered, I noticed I have a glitch. So I think I made a mistake somewhere. Oh, somehow the numbers got put in twice. Okay, my bad. Actually, I don't mind making mistakes in class because these are some of the same problems you might have. So I'm okay with that. I'm just going to have to redo this exercise. So I'm just going to clear out that BPF PSD. And let's try one more time. BPF PSD. I should have caught this, but that's okay. Okay, there's our numbers. And let's go back and replot this. Okay, so power spectral density. This is really, I should change that. Since we're emphasizing GRMS squared per hertz, let me change that to GRMS squared per hertz. That label. Well, you can see that's a bit cumbersome to write, so no wonder we like to abbreviate that G squared per hertz, but more properly it's GRMS squared per hertz. And the red spec curve and our blue bandpass filter curve line up very good. Now, we have a drop-off at this final band because this final band, the bandwidth went up to 3620 hertz. So we were unfairly dividing it over a frequency domain where there was no energy. So let's go back and sort of fix that problem. Let's go back to our table here, and I'm going to make this final. Let's see, what should we do? Let's make this. This is going to be a little awkward here, but I'm going to make the center frequency 2000 hertz, and that center frequency is also going to be the upper frequency. So in that case, here would be our final breakpoint. So it would be 0.00842. So let's see if I can do this right. Let's change that final breakpoint to BPF PSD. All right. So it's going to be the 8th row. It's going to be the 2nd column. And it's going to be that number there. So now if we go back to plot multiple curves, plot curves. Okay. Let's try that again. I've got, what it did is it overwrote, or it got superimposed on the previous plot. So I clicked out of it, closed it out. Let's plot again. Okay, well, that's better. And actually, probably what I should have done is made that center frequency 1900 hertz. Oh, I see. I know what I need to do. A couple of things. Let's make that 1900 hertz. That's roughly the geometric center. So let's change the frequency of that final breakpoint to 1900. And then close out of this plot. Close out figure 7, replot. Okay, and it's better. We get a closer compliance there. So anyways, what we've done is we've shown how we can use a successive bandpass filtering method to calculate a power spectral density. And again, please do this as an exercise. Now, imagine back in the olden days, even before I was born, and someone was trying to calculate a power spectral density using just analog equipment. Well, they might have had the data, the random data, for example, on a tape, magnetic tape, so they might have played that through an analog bandpass filter and then an analog overall RMS meter. So what that technician or engineer would have needed to have done is to adjust the knobs on his variable bandpass filter and play that tape maybe 8 different times into the through the filter and into the RMS meter, and then just written down what the reading was for the RMS filter for each successive band. And that's probably how it was done in the olden days. So I want you to appreciate that as well. Of course, nowadays, almost always when we calculate a power spectral density, we use the Fourier transform method. Okay, I'm going to park this MATLAB aside for a moment here. So there's the Excel spreadsheet, which I hope you can do an exercise where you generate that yourself. And let's see what else we have. So back to the slides, what I have is is essentially, again, I went through the same exercise as I made the slides. And again, depending on random number seed generation and all that, the time history may have been slightly different, although still having the same statistical properties. So this was the first octave band from the PowerPoint slide synthesized time history. So here it's bandpass filtered from 14 to 28 hertz, and I've carefully noted the input RMS and the filtered RMS. And we're going to do that for each successive band. So we're not going to spend too much time talking about each of these figures. You can go back and look at these slides on your own if you like. Of course, the input RMS is always going to be the same number. So there's 113 to 226 hertz in band number 4, band number 5, band number 6, 7, and then here's the band where the upper band edge frequency is well above the maximum frequency of the PSD specification. And here's the Excel spreadsheet for the PowerPoint version of the exercise. So you've seen something similar to this before, which I just demonstrated in class. Okay, and then what I did is I took the coordinate points and I read in the NavMat spec file from hard drive into the workspace, and then went and did the same sort of plotting exercise. In this case, I made the NavMat underscore spec the first array and the bandpass filter the second array. And that doesn't really matter which is first or which is second. The only difference it makes is what color each of the two curves will be. The first one's blue and the second one's red, if I remember correctly. Yeah, in fact, there is the result there. So we saw something similar in our own in-class exercise. Again, I've carefully noted GRMS squared per hertz. Well, almost always abbreviated as G squared per hertz. Okay, now we're going to switch gears a little bit and talk about another application of filtering. And sometimes we have to decimate or downsample data. And think of this like if we were going to decimate by a factor of 2, we would retain every other coordinate point in our time history and discarding the rest. So we would maybe we would keep the odd points and discard the even points. And if we did that, we would reduce that array size by a factor of 2. Well, why would we ever want to do such a thing? It could be that we chose our sample rate so high that now we're trying to take a drink of water from a fire hose. So we want to cut down on the data storage and also the time it's going to take to do our post-processing. And it could be that we're only interested in the energy at the very lowest of frequencies. So maybe we sampled our data at 100,000 samples per second, but now for whatever reason we're only interested below 200 hertz. So that time history contains many points that we just do not need. Now I'm just going to, well, let me just cover the next bullet. It's a good engineering practice to have a digital low-pass filter prior to downsampling our digital data to prevent aliasing error. So an aliasing error is where energy is mapped from the higher frequencies down about the Nyquist frequency and deposited at the low frequencies and causes a spurious error. So if there's aliasing, the levels at the lower frequency will be higher than they really are. Now I've just got a rule of thumb here, and this is not carved in stone. This is just a very rough rule of thumb. I'm going to say that the filter frequency should be less than 0.8 times the Nyquist frequency, where the Nyquist frequency is 1/2 the sample rate. And to be conservative, it's probably better to even have a lower filter frequency. So let's go ahead and do an exercise, and This is a slide I need to fix. If we want to be consistent with the previous slides, I need to change this to input_th. But in my case, I'm going to have from our class exercise Excel_th. And all of this is a way of saying we're just going to use that synthesized time history as our sample input. So we're going to downsample with a factor of 10, and we're going to low-pass filter at 100 hertz. And the low-pass filtering will actually occur before the downsampling. So let's go to, this will be time history input, signal edit utilities. And we're going to do choice number 3. This is decimate or downsample. And okay, this script downsamples a time history with optional low-pass filtering, which I say optional, but it really should be used in almost all cases. With a 6-order Butterworth filter with refiltering for phase correction, the input array must have 2 columns, time in seconds and amplitude. So preload into MATLAB, I've got Excel_th. Although in the slide version it was input_th. Acceleration in G's. We will apply a low-pass filter. And we're going to downsample at a factor of 10. And before I do anything else, let's click on the Read from MATLAB Workspace. So the sample rate is, let's see, that would be about 17,480 hertz. And by decimating by a factor of 10, we're going to take every 10th point. So our new effective sample rate should be 1700, or will be 1748 hertz. So based on this little very crude rule of thumb, our filter frequency should be less than 699.1 hertz as a good engineering practice to prevent aliasing. And let's put it at something even lower yet. I'm going to take this down to 200 hertz. So let's calculate. So here is our decimated data. And we can zoom in on this. We can take a look at our decimated data. So we have some oscillations there with fairly well-defined and rounded peaks. So that would be at a 200 hertz low-pass filter. Well, what if we put it down to 20 hertz low-pass? Well, let's see, our spec starts at 20 hertz. Let's put it at 30 hertz low-pass filter. So we're going to low-pass filter and decimate. And you can see here is a signal here. And probably if we counted the number of peaks and divided by time, it would come out somewhere around 25 hertz or so. So this is just a little tool. If you ever need to downsample your data or decimate it, just please be careful and use a low-pass filter. Okay, and the next couple of slides I'm going to show you an example where you would certainly low-pass filter, and you might even decimate as well. So what's that going to be all about? Well, so here's a supplementary topic. So let's take a launch vehicle. Now, I'm showing an Atlas V here, but I could have just as well have shown a Delta IV or an Ariane type European Space Agency vehicle or a SpaceX vehicle. And there's something called a coupled loads analysis. Now, this is a finite element type of analysis, and it's done prior to launch. And there's a finite element model for the launch vehicle, and it gets connected with a finite element model of the payload. Now, in some cases, that payload might be represented by what's called a Craig-Bampton model. And maybe in an upcoming webinar, we'll cover coupled loads analyses and Craig-Bampton models in earnest. But for just right now, let's just consider that we we're doing an overview. So the coupled loads analysis predicts the payload and launch vehicle combined response or system level response due to major dynamic and quasi-static loading events. And this is performed prior to launch. Now, after the launch, hopefully we've gathered flight accelerometer data, and we can take that data and feed it back into our coupled loads analysis and do a post-flight data reconstruction. And we can use that for a variety of reasons. We can use it maybe for updating models, both for forcing functions as well as the response of the vehicle. And here's just a couple more notes here, a couple bullets. So the flight accelerometer data is low-pass filtered for coupled loads analyses. That's typical because maybe the data was sampled at 10,000 samples per second or higher. But it turns out only the low frequency energy is required for coupled loads analyses. Now the cutoff frequency for that filtered signal from the flight data is going to vary. It depends on the launch vehicle, the payload, what were the key flight events. And we're concerned about low frequency events or loads, and these could come from pre-launch events like ground winds or seismic loads. And again, you might think, well, earthquakes and launch vehicles, how do those fit together? Well, some of our launch vehicles go out of Vandenberg, California, and that's located near the San Andreas Fault. And that launch vehicle and its payload is like a big cantilever beam sticking up from the ground. And even though during that 2-week window, 2 weeks roughly, when that launch vehicle would be on the pad for its final tests and loading fuel and whatever, during that 2-week window, the odds or probability of an earthquake occurring are extraordinarily slim. However, launch vehicle and payload together could be over $1 billion. So yes, for a Vandenberg launch, we need to do a seismic analysis. There's also liftoff events, engine and motor thrust buildup, ignition overpressure, pad release. During powered flight and ascent, there's aero loads, buffets, gusts, static elastic, maneuver loads, so on. And there's also things like liquid engine ignitions and shutdowns. Sometimes you'll hear main engine cutoff effect. There could be some oscillation effects going on. Say a vehicle, a particular liquid engine has two turbo pumps and two nozzles, so it has two engines effectively. And if those engines are shutting down at slightly different rates, then that can set up different coupling effects and oscillation effects that occur. And that can be called main engine cutoff, or if there's a second stage, there could be a second stage cutoff as well. Okay, now there's all these different standards that you can come across if you look at the NASA or the Aerospace Corporation, different guidelines. And here's just a sample one, just sort of pick this up out of a hat. So here's the European Cooperation for Spacecraft Standardization, ECSS, Spacecraft Mechanical Loads Analysis Handbook. And here's a few guidelines. The low frequency dynamic response is typically from 0 Hertz to 100 Hertz of the launch vehicle payload system to transient flight events. So typically for these larger launch vehicles, 0 to 100 Hertz would be the frequency domain of interest. So again, if we had our data that was sampled at 10,000 samples per second for our flight accelerometer data, we would certainly need to low-pass filter it, and we might also want to decimate it as well. Now for some of the smaller launch vehicles, the range of low-frequency dynamic response can be up to 150 Hertz. So again, there's some acknowledgement that there's some vehicle dependency as to what the needed upper frequency is for the low-frequency coupled loads analysis. And of course, these various NASA and ECSS type handbooks give some good starting guidelines. And then it's also a very prudent idea if you're doing a payload to look at the payload's user guide, or sometimes it's called the payload planner's guide, to learn more about what the critical events and critical frequency domains are for the particular launch vehicle in question. So let's see, that about wraps it up for today. If you have any questions, you're welcome to send me an email. And there's various emails I have, but most of them come to the same place anyways. You can contact me at tom@vibrationdata.com. And next week we're going to be doing integration and differentiation. And this will be both for time domain and frequency domain signals. So I hope you enjoyed this unit, and please do the homework, and we'll catch up with you next time. Thank you, and goodbye.